Yeah, hi everyone. So yeah, I'm Kevin, and there's a few people who. It's Max. Okay, I guess it's just me, but there's several co-presenters. We have Max, who's Michael Maxwell, who's at Golder and UBC. We have Doug Oldenburg, of course, my supervisor at UBC. Doug is actually in Argentina right now, teaching I think a course in inversion, so he sends his regards. We also have Lindsay Heggie and Saki Kang at Berkeley and Stanford, respectively. Yeah, so we're really excited. Yeah, today I'm going to talk to you about some work that I did in Myanmar last year, and also some future plans based on that foundational work to hopefully in the future. So yeah, today's talk will be in 3 parts. I think first I'll give a bit of a context for Myanmar. It's a relatively it's not a very well-known region in the world. And I'll talk a little bit about the water context. Then the second part, I'll talk about the work that I did there in 2018, and the building and the deployment of an inexpensive resistivity instrument, and the lessons that we learned from that. And then 3, I'll talk about a proposed project with Geoscientists Without Borders, or GWB, based on that work. Yeah, so let's get started with the context. And yeah, so, really things are very, there's a very unsustainable water crisis right now. So, this is the country of Myanmar. It's actually a very large country. It's difficult to appreciate on the world map, perhaps. But the reality is that, in many parts of Myanmar, and in Mao State in particular, many of the wells in the villages, they run dry for about 2 months, in April to May. So actually right now, and only 69% of the households, they have access to improved water sources, and where improved is defined as free from contamination sources. There are some statistics that I compiled which show that in 2018, about 24,400 villagers suffered directly from water scarcity. And really this poor water access, it's exacerbated by the extreme poverty in the region. The numbers don't really do it justice, but I can try. About a third of the people in Myanmar are in poverty. And if you compare even just to the neighbors, Thailand and Cambodia, 9% and 14% respectively, and they're by no means rich countries themselves. So it's a very poor country. And definitely the climate change has the potential to exacerbate the threat in the region, with the prospect of increased frequency and intensity of extreme weather events in the region, particularly from El Ninos. So the current situation is that the villagers, they rely on this kind of patchwork aid, which comes from individual donors and sometimes from government. And basically they just come into these villages with these hefty water trucks and disperse as much water as they can. But even then, it's not enough. And the typical ration is about 4 gallons per person per day, even with that aid. To give some context, that's below the World Health Organization's recommendation of about 5 gallons per person per day. And that's just for the absolute minimum for basic drinking water and for hygiene. I think we can hear it from no one better than the people themselves. So a resident of Budinkyang village, they said, water reserves dried up earlier this year, and the annual shortages have never been quite this bad. Dakin Sa says, when the water is very rare, we just need to hope for the water supporters. And on top of that, the delivery is quite arbitrary. There have been interviews with villagers to attest that the aid is not necessarily going to the hardest hit areas. It's definitely not sustainable. And I have a short video which I think will liven things up.
ဒါမဲ့တော့ခဏတော့ရမယ်လေလာပြီးတော့ပို့နေတာကတော့လေသူတို့ပို့တဲ့အပိုင်းကတော့ဝတ္တရားကြည်လောက်တယ်လို့တော့ပြောလို့ရတယ်ပေါ့ဒါပေမဲ့ရွာလူအင်အားအနေနဲ့အခုဒီဘက်ပိုင်းဆိုရင်ဒါတင်ကြီး150လောက်ပေါ့နော်
Now, for reference, this video is from 2015, but really the same thing is happening every year again and again. At this time, maybe I'll just ask, is the volume level okay? Should it be louder or softer? It's myself. Okay, just want to check. Okay, so now I'll talk a little bit about Mon State. So Mon is in the southeast of Myanmar, and basically it's in this coastal plains region, very low-lying area. For reference, so that's Mon over here, and the place that I'm sure all of you have heard a bunch about in the news, that's Rakhine State, where the genocide of the Rohingya is happening. That's in the west of the country over here, and most of those people, or I think about 700,000 documented refugees, have fled to Cox's Bazar in neighboring Bangladesh. It is a big country though, again, so it's not like that's right next door. The average annual rainfall in Malamine, which is the capital of Mon State, is about 5 meters, but that precipitation is concentrated really just in 3 months of the rainy season, and that's June, July, and August. And I can attest, the rest of the year there's essentially no rain at all. So Mon State, it's named for the Mon people. It's fascinating, really, if you get into it. There are over 100 different ethnicities in Myanmar, actually, and the Mon are one of them. And they actually have a very rich history, recorded history dating back over 1,000 years. And they've also been said to be one of the primary cultural influences for the overall culture of Myanmar and Thailand, and particularly for the spread of Buddhism in the region. There are a variety of ethnic populations and minorities in Mon State, not just the Mon people. You also have the Rakhine and the Karen, and many others. You also have the Bamar, who are the ethnic majority. So if you hear someone say that they're Burmese, it's actually very complicated. Do they mean that they're just from Burma, or are they the ethnic majority? It's not really easy to tell. But really, there's been a lot of conflict between the ethnic majority Bamar and the various minorities over the past several decades. The contemporary civilian displacement in Mon, it dates back probably centuries, but the most recent conflict was in the 90s. The result of which was that tens of thousands of refugees had to flee to Thailand, and many of them still remain there. To this date, there's still about 35,000 IDPs, or internally displaced peoples, in Mon State. And that said, it is actually one of the more stable and peaceful regions in Myanmar, and there has been at least a formal ceasefire since about '95, with only intermittent clashes in the interim. So in terms of the status quo when it comes to water, many villages, they rely on groundwater. There are also rainwater catchment ponds. And the thing is that because there's actually a high water table in much of this coastal lowland, there are lots of these pretty shallow hand-dug wells. And the problem is that most of these wells, or at least a good number of them, they go dry during the dry season. And there are also problems with saltwater intrusion into this shallow aquifer. So the government drillers, they actually prefer to drill into a second, deeper aquifer, which typically occurs at 20 to 70 meter depths. And they have a pretty large budget as well allocated to this, almost $1 million USD. The problem is that they don't really use very many scientific or hydrogeological or geophysical techniques to help them find the places where to drill the wells. The result of which is that their success rate is pretty limited, only about 60% in drilling viable wells. And I would attribute this to the fact that the engineers, they lack any fundamental knowledge really of subsurface hydrology or geophysics. And there's a pretty weak talent pipeline in higher education. At the local university, they don't have any equipment. They only have like one module from one course that's devoted to geophysics. And I've spoken to the head of department there, and they said that they're quite lacking in geophysics. So of course, like, we're not operating in a vacuum. There are other organizations that are trying to do things. The biggest one is probably UNICEF Myanmar. The thing is that they've done a few surveys in the past years using a Siscal R2, so 1D VES. They haven't made any attempts though to build the capacity in the government itself. It seems like it's mostly a top-down effort. And the same can be said for the Japanese International Cooperation Agency, or JICA. They also did some surveys with a Siscal in 2017. But similarly, there have been no capacity building efforts. Interestingly, the national branch, the national branch of the DRD, they also do some work with 1D VES, but their efforts seem to be preoccupied with the central dry zone in Myanmar, which tends to have worse water crises and droughts. And the water table, I think, is as much as 400 meters deep in that region. So they have less time really to be able to devote themselves to Mon State, where the need may be less comparatively, but is still great, of course. In terms of the hydrogeologic context, this is a generalized strat diagram that I and Sagi we collated from various well logs from the Ministry of Agriculture and Irrigation. So basically, there's topsoils and alluvium and laterite deposits. And then the shallow aquifer I mentioned is the sand aquifer, typically 3 to 15 meter depths. Underlying that, we have a clay aquifer, which is less commonly a lateritic or sandy clay or sandstone. And then underlying that, the bedrock is typically a slate or granite. The region is actually famous for its slate. They actually still use slates to draw on in classrooms, although that's being phased out quickly. And really, the target of interest is these fractures in the bedrock. And typically this occurs at 20 to 70 meter depths or even greater, according to these well logs. As I mentioned, saltwater intrusion has been observed to be a problem in the shallow aquifer. Yeah. Okay, so that's a bit of context, and now I'll get into, I guess, the work that I was doing over there. So basically, I was recruited by this organization called Kusa International. They were started in 1961, so they have quite a history, and they're sort of the Canadian analog of the Peace Corps, for those of you familiar. Basically, their mission is to eradicate poverty and inequality around the world through the efforts of skilled volunteers. So I was recruited as a geophysical survey trainer and consultant, and I was there from 6 months, from about June to December of last year. So I was working with the Department of Rural Development, that's their logo over there, in Mon State at their capital office in Malamine. And really this all started because the Mon DRD, they had expressed a desire to use some old geophysical equipment that they had in order to find water. But their engineers apparently didn't know how to use the equipment. Of course, that's a very pretty story until shortly before I left, I found out that they didn't actually have any equipment. So, at that time, I think I was a little bit ready to just jump the ship. It doesn't really make sense to go over there with no equipment in hand and no prospect of getting some. It would just be a waste of everyone's time. But what happened was, I was kind of desperately searching through papers online, and I came across this one by Dr. James Clark and collaborators at Wheaton College. It's called Inexpensive Resistivity Instruments for Groundwater Exploration, Experiences of African National Geophysical Teams. Bit of a mouthful. But I think that, Dr. Clark, he has this really beautiful vision, which is that he wants to democratize geophysics and make it accessible. Typically this commercial equipment that's in the tens of thousands of dollars USD, it's just unaffordable to developing country governments and private well drillers in those countries. So he had a few key design considerations given that. The first is that it should be relatively inexpensive, only a couple hundreds of USD. Second is that it should be simple to build and understand and also repair in what are often remote field locations. Of course, it should be robust in the field, and it should be relatively easy to transport it by air. So pretty light and portable, with no large batteries. And actually, he's already done some work in collaboration with Water4 in Africa. They've been to lots of countries, Togo, Mali, Ethiopia, to name a few. And they've been able to successfully site over 150 wells using this technology. And they had an 86% success rate in determining whether a well would fail or succeed. So I got in touch with him, and he actually was generous enough to give me instructions for how to build the device. So this is a circuit diagram. It's a bit messy, I apologize. But this is a circuit diagram developed by my friend Henry Mack. I myself, I don't have that much in the way of electrical experience. So he's an electrical engineering grad. He graduated at the same time as I did, and a good friend. So we embarked on this endeavor together. And the basic idea is that there's a DC power supply, and then that goes through an AC inverter, about to 240 volts AC. We were actually able to find a 300 volt AC inverter, so even better. In turn, that goes through a full wave bridge rectifier in parallel with a 1 microfarad capacitor, and that brings that AC up to about 300 volts DC, a high steady voltage. And then the other key component is that there's 2 switches, a double pole, double throw. And then you can flick those back and forth, and the idea is that reverses the voltage, and that mitigates both the buildup of charge, and also it's supposed to mitigate SP. And now I'm going to show you what the fruits of our labor are, after much blood, sweat, tears, and solder. It took a lot longer than advertised to build this. I cannot understate that. But as you can see, it's pretty simple. And these these electrodes here, they go to the A, M, N, and B electrodes in a 4-point best survey. And then there's 2 electrodes where you insert a multimeter and you measure the voltage, and then the other 2 for the current. And from that you can get resistance and resistivity. Here are some of the other parts that we were using. So these are just cheap multimeters from Lee's Electronics over on Fraser, I think, about 20 bucks each. Some lag screws from Home Depot, about 8 inches long. This was a bit hard to find, but 14 gauge wire, about 300 meters long. And we cut up that wire into 4 parts, 100 meter, 100 meter, and 50 meter, and 50 meter. Then some cheap plastic measuring tapes, some cord reels, and then these inverters, which are actually from Kenya. And then they came to Texas, and then they were shipped to Vancouver. And that's a long story, but we were able to get those just in the nick of time, actually, before I had to depart to Myanmar, so that was really lucky. This is the whole setup with the addition of a car battery that we were able to get in Myanmar. And all told, the setup is about 500 USD, and as you can see, it fits in a suitcase, although it's about 70 pounds. Here's some pictures from the actual training that I did in Myanmar. So here we have Kay Kan Win. She was an engineer in my training group. I had about 15 people in my group, and they were typically junior engineers from the Mon DRD office and also from the townships. In Myanmar, there's the state level and then the township level. So Mon State has 10 of these townships, and we had some of the engineers from these outlying townships come in for the training. And then typically I would have just a couple hours a week with them. So not that much, because it was all on top of their other normal duties. Here you can see everyone hard at work during a 1D training session in inversion. Basically, it's a simple Monte Carlo inversion that was produced by Dr. James Clark, and I don't believe it's open source, but it was free. So that was the big draw. And then here's the field setup, and the multimeters measuring the voltage and the current. Well, I guess one of them isn't on. So I can share a few general observations that we had from our shoestring budget, as I like to say. The first is that we used a Wenner array just for simplicity. The second was that I actually arrived right in the heart of the rainy season. So it was with great difficulty that we tried to waterproof everything. This was exacerbated by the fact that the inverters, they had these big holes in them. So I tried to come up with some creative solutions, but it was really difficult to waterproof them completely, and they would tend to short circuit very easily. And unfortunately, we wasted a lot of time just trying to fix those. Another is that the plastic measuring tapes were pretty cheap and they tore easily, so we had to fix those several times. I guess the positive is that the current readings with the multimeters were generally very stable. Typically they were in the 10 milliamp to 100 milliamp range. The thing was though that the voltage readings were very unstable, about 10 millivolt to 10 or 15 volt range, those measurements. And so when I was doing training with my participants, it was sometimes hard to tell them a single value to record. It's a bit arbitrary. Generally, there was a high value for SP, which we just measured when we reversed the voltage, about 10 to 100 millivolt range. And there was a high degree of spatiotemporal variation with that. Another thing we observed was that for large AB spacings, generally the signal-to-noise ratio was quite small. What tended to happen is that, so like the resolution for the multimeters is only about 1 millivolt for these cheap things. And at large AB spacings of maybe 200 meters, the measured signal voltage was as little as maybe 7 or 10 millivolts. So really getting close to that threshold. And that was exacerbated by the high SP. I'll just leave this here for maybe a few seconds just to provide a little breather. This was actually a slide that I showed during my training, and I just put it here because I think compared to North America, there are actually a lot of cultural differences with Myanmar. I'm happy to elaborate after the presentation if you're curious. One of them is that the office culture, everyone is always laughing or telling stories or eating snacks, or it makes us look like robots in comparison, to be honest. So I guess I like to think, using humor, it was one way to kind of get through with them and to connect in what was often a very low communication environment. You think to yourself, only 4 years ago, this place was essentially North Korea, anti-democratic, and it really just very recently opened up. So they're very much not used to foreigners and to foreign English or any English for that matter. So even though they do, in the higher education system, they do actually use English for almost all of their courses, the people had like a lot of difficulty understanding me, even when I had a translator. Now I'll show a little bit of data. So this is just a 4-point resistivity survey. On the left is the data produced from our instrument, and the right is the data from a Syscall R2 done by a JICA survey in 2017. And this was at the same location in a place called Jaw-in Village. So as you can see, down to about 35 meter depths when you're doing the inversion, the shape of the curves are pretty similar, although there's a bit of displacement in the actual magnitudes of these observed values. I think for me though, this was a little bit of confirmation just that we were not measuring complete junk. It's a busy diagram, but basically this just outlines the procedure that we used for inversion and interpretation using this software. This software is called VES Inverse, and it's free. So the basic idea is that you select a certain number of layers, at least 2, and then you create these little boxes, and 1 box for every hump. That's what we would do. And then you fit the box to get a thickness range and a resistivity range for each of the layers. And then after that, it's Monte Carlo, so just a million inversion, or a million iterations or so, and then it figures out the model with the minimum RMS error. And then you get, in this case, a 4-layer model. So here's an example of that data set that you just saw from Jaw-in, and then applying that methodology to here. So here we decided on a 3-layer model, because that tended to produce the lowest RMS error. And just to lay out this plot. Basically, the red points are the actual data. The blue is the inverse model. And then the black is just the layers plotted on, if this is thickness, and then this is resistivity. And then if we interpret that final layer as the water layer, then we get a depth of water of about 11 meters. And this is in the general neighborhood of the 16 meters that was predicted by the JICA survey performed at the same location. Here's another quick example, just at a nearby park called General Aung San Park. And we got 6-meter water depths with that final layer. And then we did a water level measurement at the DRD office, which is just a couple hundred meters away. And the water level measured there was 9 meters. So again, the same general neighborhood. Here's a survey that was definitely a bit more enigmatic. So this was in Kong Tale village in Baleen Township. It's still in Mon, but definitely a ways away, about 3 hours. We actually tried to go to another location where the JICA data, where there was JICA data, which is very close to here, just a couple kilometers, a nearby village called Awanji village. But it turned out that there's an ethnic militia called the KNU, or the Karen National Union, and they had control over that area. So we unfortunately couldn't get the permissions to go there. So this is the best that we had, which is close by. And the problem is you can see that things are pretty unconstrained at depth. I don't really think there's enough points to constrain that curve. And I think this is when I realized that it would be nice to have an instrument with larger depth of penetration. Dr. Clark's design is really great in African contexts, where the water table is a lot higher. And I think that's why it's been so successful there. But definitely in Mon State, the well logs show that the water goes a lot deeper. So maybe just to quantify that a bit loosely, there is a module in Dr. Clark's software to do sensitivity analysis. So we would do the simple procedure where we would take each parameter and then just vary it, and leaving all the other parameters constant. So for instance, the thickness of the first layer and then the resistivity of the first layer. And then we would see what variation in that parameter value would be required to increase the RMS error by 10%. And that's just an arbitrary number, of course. And so if we apply that procedure to this Tonkale village data, then we see that for the last layer, the resistivity is quite uncertain, about 81 plus or minus 33 ohm meters. So towards the end of my placement in October and November, I was trying to increase the depth of penetration. As you recall, one big problem was the low signal to noise ratio at the large spacings. So one thing I did was I bought a more expensive multimeter, or the DRD paid for it actually. And this multimeter had, I think it was 0.01 millivolt resolution. We also got, we were fortunate to get a donation for a much longer cable. And it was a pretty thin cable, about 20 gauge. But we were out of budget for more cable, so that was actually a blessing. So on my last day, we were able to do a survey, again in Jawan Village, although a bit of ways from the original survey location. And these are the results. And we interpret the depth of water as 28 meters, and that's in the fourth layer over here. That's the inverted results. So I can summarize some kind of soft lessons that we learned. I call them my 7 Ps. The first is that progress will be slow, easily 2 or 3 times slower than one would expect it to be. The second is that there's the face-to-face communication is really powerful in what is often a low communication environment. My boss, he would almost never check his email. If I ever wanted to get anything done, I'd have to get a meeting or I'd have to see him. And that was just the reality. Another is that pictures were really essential to be able to get my points across. Equations, there was very, very little traction. Practice makes perfect. Definitely if I could go back, I would just wish that we would just do more brute repetition of things. Surveying 10 times or 20 times, running through the inverse software 10 times, 20 times. because I felt with the low communication, the understanding was pretty limited. Another is that partnerships with the local stakeholders. Only later we came to realize this is really important. All these other actors like UNICEF and the national DRD, we realized they were doing other things that were very much related to what we were doing, but we didn't realize until several months in when it was really too late realistically to change course. So that was counterproductive. Another huge one is that all of you know this well. Geophysics is not a panacea by any means. It's not magic. But it was very difficult for me to be able to express this to the government officials who wanted just a one-shot wonder, right? And I think the most important lesson is, how do we teach perfection? Like I gave a mini version of this talk at Sajib, and someone raised this question, and it's a great question to which I don't know the answer. When I was in the field, I think all of my engineers, they were always disappointed when something would break, or the data was more ambiguous than they would have liked. So if you have any ideas, please let me know afterwards. That's very much an open question. Okay, now on to our final part, where we'll talk about our proposed project, future. So I think this previous work, it demonstrated that DC can work. It can delineate low resistivity zones, and we were able to establish some partnerships with key stakeholders in the water space in Mon. Definitely, though, it reveals the need for deeper penetration equipment. Definitely at least 70 meters, 100 meters would be more ideal. As well as the ability for 2D and 3D imaging. We observed a high degree of lateral heterogeneity. And this would also help with the saltwater intrusion, trying to characterize that. Another huge thing is that, of course, we need ground truth. And unfortunately, when I was there, I wasn't able to get any. And this is because at the Mon DRD, their drilling season starts in around December and lasts for a couple months. But I left right before December. And also there was a kind of budget hiccup. So they couldn't actually drill where I wanted them to drill. And that was unfortunate. So we proposed a one-year project to GeoWB to capitalize on this initial progress. And to that end, I think we have a really strong suite of partnerships in our consortium. So of course we have UBC-GIF. We have Max as the project director. We have Doug Oldenburg as the project sponsor, and myself as the project manager. From Mon DRD, we have the director there, Mr. Somong, who was my boss when I was there. And we also have the participation of the local university, their geoscience department. So we have the department head of that geoscience department, Dr. Yin Ai, and we also have Zalwin U, who is a assistant professor there and also a PhD candidate. We also have great participation from Stanford and Berkeley, from Sagi Kang and from Lindsay Heggie, and they've been really instrumental on putting together SimPeg as lead developers. And they have a lot of expertise, I think, in geoscience education and interactive online activities to support that. So I'm really happy they're on board, and of course we have Golder represented by Max, and they'll might be able to provide some in-kind contributions and provide consultation. We also have Melanie Stevens, a friend of mine. She's from Tech, and she'll be able to provide any mapping support. And I think it's important to recognize that really the local stakeholders, they're the most important. Long after we're gone and done with the project, they're the most essential to sustain the impact afterwards. So we have a few objectives for our project. Basically, we'd like to perform at least 20 geophysical surveys in high priority and water stressed areas throughout Mon State, and we expect that this will impact about 15,000 people directly by alleviating water scarcity. In terms of picking those places where we're going to do surveys, we're going to use UNHCR standards, which are pretty typical according to Paul Bowman. So the first is we're going to drill in places where the existing wells are either non-functioning or of low yield, less than 0.2 liters per second, where there's no alternative safe water source that exists within at least 500 meters for the most distant household, where more than 250 people are using the same well, and where the existing wells are close to contamination sources, such as latrines or stockyards. We're aiming to increase the well drilling success rates by at least 20% from a baseline of about 60%, according to estimates from the DRD, and ideally to 80%. We're going to train an estimated 23 engineers at the Mon DRD, as well as about 20 students, including graduate students and undergrads, and professors at the local university during a 2-week training. Yeah, we are hoping to inspire the students at the university, hopefully to pursue careers in geosciences or become water professionals themselves. And of course, we're aiming to develop a comprehensive suite of open source educational materials for ERT, which is our chosen method. We have a few parameters of interest. We have depth of bedrock, we have aquifer depth and thickness, and we also have the lateral variability in those parameters. And we're also interested in the presence of saline water. Right now, we're definitely still exploring, but we would aim to procure something like a Syscal R1 Plus with 48 to 96 electrodes with 10-meter takeouts in order to get the depth of penetration that we want. And of course, that's very budget dependent. We're expecting to hear back from GWB in about a month with the status of our proposal. So we'll see then. And the core of our program really is this 2 weeks of intensive training in November of this year. To that end, we're going to be developing a host of educational resources. There are lots of them here. I won't go through them all, but one of the bigger ones is this 50-page user guide, which will, for troubleshooting and data acquisition and analysis for ERT. And then a lot of these online and offline resources, including Jupyter Notebook apps. And many of these have already been developed at GIF. The second is that we're planning to use SimPeg, which is simulation and parameter estimation for geophysics, also developed by GIF. But it's definitely tailored more towards research users, and we'd like to develop a lot of additional documentation to tailor it to the non-research users. And really there's this whole ecosystem of open source resources that we're building upon for this project. We have EM GeoSci for electromag. We have these Jupyter Notebook apps, which were developed for UBC EOS 350, which is the intro geophysics course at UBC. And of course, Doug's DISC lecture in 2017, he did that in lots of developing countries. So that will be an invaluable experience for us. How are we doing for time, Ross?
I have a
Okay. Yeah, so this is a little bit about SimPeg. I'm sure many of you have already seen it before. But basically, it's a modular, extensive multi-physics framework. The back end is done in Python, and it's on a finite volume discretization. And so basically, you can simulate and invert ERT data for a wide variety of meshes, including tensor, curvilinear, octree mesh. So the general plan is that we'd start off things, or there'd be a long preparation phase, of course, but on the ground, we'd start off in early November with the 2 weeks of training. And this would include both a lot of field demonstrations and 1D and 2D surveys, as well as a good deal of office work and computer lab, getting everyone familiar with SimPeg. And there'd be lab translation by this gentleman, Jodamoy Annan. He was actually my translator when I was there in Myanmar, so you already know him. And then the idea is that after this, this would be led by Doug, by Max, and myself. And then after that, Doug would go back, Max and I would stay, and basically we would select the top 5, the best 5 performing engineers from the DRD, and we would select them as TOTs, or trainers of trainers. And for them, we would do a lot more in-depth training. So we'd start out by doing calibration surveys at about 5 villages with productive wells in order to figure out what the signatures of those are. Then we'd follow that up with 5 to 10 surveys in high-priority villages. And around that time, that's actually when the drilling season starts at DRD, so it's good timing. The DRD, they would go drill in 5 to 10 villages. And they have a lot of budget and responsibility for doing drilling. They also have actually a lot of water quality testing equipment, and they test for typical things like TDS and arsenic and chlorine, as typical standards. And the idea would be we would get well logs and then in turn correlate the data with the geophysics and further refine the interpretations. Into the new year, January to mid-March 2020, Max would go back and I would stay on. And the idea is we would, with those 5 trainers and trainers, we'd continue at least an additional 15 surveys. We'd also hope during this time to collaborate with the grad students at the local university. A lot of them actually are already doing hydrogeological research. There's one who wants to make a map of the whole state. There's another who wants to do geothermal research, actually. There's a local hot spring. And I think definitely geophysics can contribute to all those goals. So, really our vision is that we want to be able to have a long-term humanitarian impact. And this is with the recognition that the greatest potential for change, it comes from the people themselves, not us, ultimately. And so we'd like to be able to empower them to take hold of their own future when it comes to water. Primarily in our project, that's enabled through these trainers. So one thing is that we leave the equipment with the Department of Rural Development, and this enables them to take that instrument and then train future generations of engineers at the DRD. It's our hope that this establishes in turn a statewide government training program. And potentially we can even scale to Cayenne State, which is just to the east of Mon State. And they have very similar systematic problems with periodic water shortages and no geophysics to speak of. And we also hope to generate case histories. And I think that would provide a benefit to the global geoscience community. Overall, I think our project is, the big strength is that it offers a comprehensive solution. It's not just geophysics in a vacuum. By partnering with the Mon DRD, we also have the water quality testing, we have the drilling, to drill in the places where we say are good from the geophysics. And we're also building the talent pipeline at the local university to promote the geophysics in the future and helping to build capacity in the water sector. So at the university, we would aim to support the hydrogeology research, as I mentioned, as well as the teaching capacity. So the course curriculum from their applied geophysics course is actually 15 years old, so we'd hope to be able to collaborate with them and help update that. And we'd also really love to develop a potential field camp held jointly between the government and the university. I think at this time, I'd really like to just acknowledge the people to whom it's due. First, of course, is my friend Henry from UBC, the electrical engineering grad. Without him, we wouldn't have been able to build the instrument, of course. Also, UBC GIF for their countless advice. Also, Randy Jones, he's a fellow from Water4, and he'd actually been using this cheap instrumentation for, I think, 7 years. So he had a lot of tips for me. And of course, James Clark, who I think is really visionary and wants to democratize geophysics. Paul Bowman, he's done a lot of other humanitarian water projects. He also had lots of advice for me. And Choi Sanong, who is at Kusa International in Myanmar. He was my program manager, and he ensured that logistically everything ran smoothly so that I could focus on the geophysics. Okay, yeah, that's all. Thank you very much. Are there any questions?
I don't think I saw in your case examples there the saltwater infiltration. Was there an example like that, or can you describe it, what you'd see?
Yeah, so I didn't see any studies on it myself.
So it wasn't really happening in that village you were doing this survey?
So one of the townships called Pong is right up against the coast, and I think it was reported that most of the wells there that there was saltwater intrusion. I don't think there have been any efforts to map it or really study it in depth.
So you'd be staying away from those particular problems. You do this next phase.
Yeah, I mean, I'm not sure if Max has an opinion, but definitely we need to think more about that.
So what was your main limitation of the voltage of your transmitter or your receivers? Your voltage?
I think receivers. Yeah.
It'd be really easy to buy a cheap A to D converter probably and get a lot better than the voltage.
Sorry, in A2D?
It'd be probably easier to get a cheap A to D converter and get a lot better signal to noise than the voltmeter. Because voltmeters
Oh,
are
really?
mostly 8-bit when you get up to 16 bits. You'll probably go.
Okay. Yeah, I mean, the kind of the future of this cheap technology, you know, as I mentioned in the future project, where it doesn't seem like that's going to be a part of it. I know there are other people who are kind of taking up the mantle of that cheap equipment, like Dana Sirota at she's a master's student at Mines. I think for me though, it seems like there's still a lot of work that needs to be done, and at least right now that's not my mandate. But it's interesting, of course. Like I hope it goes well.
So you're graduating to a full ERT type of survey with some sophisticated equipment.
Yeah, I guess the other thing is there's actually some people have tried to make like a cheap ERT instrument. Although it seems like you had to compromise somewhere when it comes to cost. You know, you could make it fully manual, but that takes a long time.
One of the big hurdles in this is just the cable for 48 channels.
Yeah, for sure.
Charge a major expense.
Yeah,
Maintenance problems and everything else.
We used to use the Ethernet cable. The Ethernet cable is pretty easy to come by. It's got 8 conductors.
That would be a great idea.
If you go both ways,
Oh, really?
you get 16 dipoles.
Rather than buying the Cisco cables, that'd be a smart way to go.
It's really cheap. It's all
Right,
right.
exactly.
Do you think you could actually design a system like that for less than
We've used it.
less than $1,000?
Less than what?
Less than $1,000 for the
No,
unit and the
you-
cables and.
This goes with the Cisco. You have to buy
Yeah,
the system.
right.
But we're just discussing a cheaper, simpler way of handling
Well,
the cable situation.
What's a Cisco?
Depends on the system.
Sid, what do you, I didn't hear who you said, or which cable you said in the first place there.
Huh?
What were you saying for cables?
Yes, Ethernet
Ethernet
cable.
Well, we use
Yeah.
Cat5 all the time too. So.
Yeah,
Yeah.
we use it all.
Yeah, the only problem is the insulation, depending what quality you buy, is 300 volts or 600 volts. However, we've never had a problem with any of it running underground, even in salt
Yeah,
water.
yeah.
So, yeah, that's fine, and that's an option that we have too for doing this. The plan right now is to, probably use Arrows to produce some cables for us if we get the full on funding for a 48 system. So Kevin has approached a few different manufacturers, and we've talked to them too, so Iris and AGI. And there's a multi-channel system, an old 48 that's available, that's been reconditioned anyway.
There's an outfit in Australia that has an ERT system. What are they called? Z something. Have you checked them out?
We haven't
Yeah, I was looking at them when we were trying to do an ERT survey. They have some pretty good equipment, fairly inexpensive.
yeah.
There's another alternative, the AIG and Iris.
Okay.
But what kind of voltage is it offering?
The 48 or the 48 one that they have,
Yeah.
I think that was a 500 or 600.
Yeah.
Wasn't it?
I think, yeah,
I've
about
used one for a long time.
600 volts or
600?
1200 peak to peak.
Yeah, it's,
I think that'll be more than enough. I think for
It
our.
should do for the depth that
for-
we're
yeah.
see there.
Like 100 meters.
Well,
100 meters is your maximum there?
Yeah, I think that's what we're aiming for.
And we'll probably use Cat5 cable purchased locally to get greater distances than the 500, probably 5-meter cables will end up with.
How many actual surveys did you do of this cobbled together equipment? I mean, how many, you put it in line kilometer terms or number of stations or? soundings rather?
Yeah. I'm not sure about line kilometer.
Well, soundings.
I can say discrete surveys was about 8 to 10,
Right.
something like that.
And what's your plans with this ERT? How much territory are you going to cover? You said like 15 different.
Yeah, I think including the calibration surveys, I think more like 20 or 25 surveys.
But those would be, those would be a kilometer long or something like that.
Yeah, that makes sense.
Yes.
We'll know in November.
So you really are ramping it up quite a bit. This is a big step up.
Yeah, it is, I think. I mean, one other thing is that, when I was there, just the equipment was breaking all the time, unfortunately.
Right.
And
Oh, it does.
sorry.
The geophysics program, it always breaks.
Of course. But the engineers themselves, they also had a really busy schedule, and sometimes I just couldn't do anything with them for a month at a time, because this is in addition to all their other duties. So, I mean, I don't know what you can do about that, right?
Did you have good buy-in from the local leaders? Like I see you've got buy-in from the government organizations, but even just like the local villagers, did they think that this was something that was worthwhile, and did they believe in it, I guess?
Yeah, that's a great point. So that wasn't the focus when I was there. Definitely the next time around, that will be a focus.
A corollary to that is, I've done these little resistivity surveys for groundwater, and invariably, some local will come up and say, I got my dowser, I can find water better than you can.
That didn't happen to us.
That
but,
didn't happen to you? They don't have dowsers?
I think people use them, but I didn't see it. Yeah.
They didn't bother you about it?
Yeah.
Yeah.
Yeah, I mean, it's a really worthwhile thing you're trying to do, so I think that's terrific. But I guess my concern would be the huge leap you're making now from the very simple equipment, and everybody understand why that would be worthwhile to try and make it work with a simple gear. Move it to the much more elaborate gear. And then you're very much dependent on that one system working, being able to train people to use the much more sophisticated equipment. So it's just a huge jump from what you started to do to this next phase. I mean,
Yep.
I hope it goes really well, but if that one instrument fails, you're really exposed. That'd be my concern.
Yeah.
I'm sure you've thought of that. You better get
No,
to
it's an excellent point. I've been in talks with Paul Bowman, actually, and I think he has a number of ABEM lens systems, which he would be willing to sell relatively cheaply. So if we could get multiples
Yeah,
of
you
those,
need
I
some
think that would,
backup,
yeah, or like extra cables. I mean, extras of everything. Yeah,
Exactly.
that's essential.
Well, the cables you can fix.
Back that up, Kevin approached Doug initially after he was doing this work, and when he was back here in Vancouver. And Doug talked with me, and so that's, we think it's a great thing that Kevin did over there on his own initiative. And so happy to back his energy and joining along with him to try to push this. So the geoscientists without borders has been receptive. We'll see what happens in the month.
Well, you have to come back next year and give us the.
Why that be something? Yeah.
Any other questions?
And the drilling people, the departmental drilling people, are they going to be willing to drill what you say? Have you got it to that stage where they're believers, they're on board? Who decides where to drill now?
So I can't say I completely understand the process because it's in another language and it's really Byzantine, to be honest. Right before the drilling season in December, the preceding 2 months, there's a long tender season. I think basically the various village and township representatives, they come to the office and they're trying to make their case for why to drill in our village versus the other one. I mean, I have at least tentative buy-in from, there's a fellow, Mr. Win Nai, and he's the deputy director at the MonDRD. And at least when I've spoken with him, he said several times that he will, don't worry about it, I'll take care of it, we'll drill where you want us to drill. Whether that actually happens, of course, that's another thing.
Have they ground truth any of your surveys yet?
One of them, I heard they were supposed to about a month ago, although I didn't hear back from them. Aside from that, just kind of doing surveys in the same locations as the other surveys, that's about the best we have currently.
Great, awesome. Well, thank you, guys.
Thank you.
And if anyone would like to ask any more questions, I'm sure a group will head to the Moose for a beer.